Hey, it's Dr. Brad with some exciting black hole news. Yes, we do get some black hole news. And firstly, some colleagues of mine, led by Chris Onken, have discovered the biggest, fastest growing black hole in the past 9 billion years of the universe. So this thing is so massive, it is 500 times bigger than the supermassive black hole in the center of our Milky Way galaxy. And it is so hungry, it eats about an Earth per second. Now that's a lot of food. So how do you get a black hole this big? Well, firstly, we need to know the different types of black holes. Yes, there are types. And we have three major ones. The supermassive black hole ones, like this, the ones that reside in the centers of galaxies. So this is in another galaxy, not our Milky Way. The intermediate mass ones and the stellar mass ones. Those are the small ones that are essentially the birth or the beginning of a black hole when a star over 10 to 15 times the mass of our sun explodes. Now, all of these black holes normally operate essentially the same way. The biggest thing that it dictates, and this is why this one's exciting, is black holes need to feed. And so firstly, you may be wondering, well, how does this all make sense? How do you actually see a black hole? And this is actually due to the feeding process. A black hole is sucking in gas and stars and planets and whatever else may be around it. And as the stuff goes around it, it starts to swirl and heat up and glow. So you don't actually see the black hole itself. You see all the stuff spinning and swirling around the black hole and sometimes being shot out of the black hole in giant jets, kind of bouncing off the black hole. And this glow is what we detect for seeing these black holes throughout the universe. So yes, we don't see the black hole directly. We see the buffet the black hole is having in space. Now, the fact that this black hole is eating is exciting in itself, but really, it's telling us a lot about the universe because black holes need to feed. If they don't feed, they die. And we always wonder, how do things like this get this big? And this is why the fastest growing part is exciting here. It takes time for black holes to grow from the beginnings of the universe to today. And so for some reason, some black holes grow faster and eat more and some don't. And so the more it eats, the bigger it gets. So it can eat more, so it can get bigger, and so on and so on and so on. So by finding the bigger and fastest eating black holes, it tells us a lot about the beginnings and the origins of the universe, in particular, the origins of these black holes in the universe. Now, the other exciting bit about this is potentially you at home can see it yourself. Now, you do need a fairly decent sized telescope, at least 12 to 14 inches wide. So we measure telescope in terms of how big the mirror is. So this telescope is about a foot across. That's the size of the mirror, not a foot long, a foot across. So it's not really a small kid's telescope, but it is a telescope that some keen amateur astronomers at home may have. And so you can check out the coordinates listed in the comments below and try and see if you can find this black hole yourself. And I do know a few people who already have taken an image of this from their home setup. And with the home setup, you're only going to see a faint, small, fuzzy dot, which is just the entire galaxy. So how did Chris Onken and his team find it? Well, firstly, their telescope sky mapper is 1.3 meters across, and using colors of how we know black holes kind of look and behave, they're able to get a kind of a target list of potential good options. And then by monitoring this black hole with this big telescope, you can see some of the variation just in the color or the brightness. But it still requires even more equipment. They had to get to even bigger telescopes and break up that colors of light to measure the individual elements. And when you look at some of these specific elements, you can see changes in what we call emission or kind of gas being shot out in these very specific types of elements that we're able then to detect that a black hole indeed is there. So it requires a lot of work between lots of huge telescopes, lots of techniques just to find this monster. And in another black hole development on the other end of the black hole scale, a small rogue stellar mass black hole floating around in our Milky Way galaxy. Now, it poses no harm. It's about 5,000 light years away. To put that in a scale, our Milky Way is about 100,000 light years across. This is about 5,000 light years away. Poses, again, no harm other than just being really cool to look at. So there are these supermassive black hole ones that we just talked about. And then there are these baby ones, these stellar mass black hole ones. And we think when a star 15 or 20 times the mass of our sun dies, some of the inside of it can be squished down into one of these tiny black holes. And these black holes can range in size anywhere from 1 to 2 times the mass of our sun to 6 or 7 times the mass of our sun. That's still really big, especially when you squish it down into a small, infinitesimally small point. Now, this one was measured to be about 1.6 to 4.4 times the mass of our sun, so still pretty big, but really tiny. Now, we don't see these black holes that often because, A, they're not feeding. Unlike those supermassive black hole ones, they're not big enough and have enough stuff around it to swallow it in. And it's that swallowing in process that really tells us and allows us to see them. And because this black hole is kind of by itself, there aren't a lot of other stars to feed on. Now, generally, we find these black holes through a technique we call microlensing or gravitational lensing. And this was originally a factor, a prediction of Einstein's theory of relativity. And that is, if you take a massive amount of anything, i.e. gravity, it can bend light. It can act like a cosmic magnifying lens. And so with these small black holes, you're not seeing the feeding process, you're seeing it move in front of another star. And as it moves in front of another star, that black hole magnifies through its gravity, bends the light of that star for a very small period, but it kind of tells us like, hey, I'm here, come look at me. And we can then measure the power of that black hole, its gravity through how much light and how strongly it's being bent. Again, kind of measuring the size of the magnifying glass there. Now, again, this technique has been used multiple times, but it's really hard to find because you have to have the right alignment of the black hole passing in front of a star. And if there's these black holes that are kind of by themselves, they're not passing in front of those stars that often. And this is really important because we predict and calculate there could be tens of millions of these small black holes just in our own Milky Way. Again, they don't pose any harm, but we think that they're quite common. But obviously, we only know of a handful of them. So not only is this technique important for showing and discovering them, but if these are black holes existing in kind of quieter, not a lot of happening places in our black hole or in our Milky Way, then it can really give us an insight into how many of these black holes do exist. And some exciting future black hole news predicted to come from the James Webb Space Telescope. This is NASA's new big telescope. Its mirror is much bigger than the Hubble Space Telescope, and it's just coming online. And so by having a bigger mirror, it'll be allowing us to see fainter light and further away objects. And what this telescope is aiming to do, one of the many things, is look at some of the baby or what we call primordial black holes in the universe. Now, we know these black holes are there, but because they're so far away and generally so much smaller, we can't really see them. We only can really see the giant, big ones that have lots of stuff going around it. We can't see the smaller, fainter, kind of quieter ones. You check out Google Maps and you zoom in on your house, right? And you'll see your house, you'll see maybe your car and some detail, but that's about it. If you had a bigger space camera and a better camera, you'd be able to see just some of your flowers or maybe some of the mess or some of the toys left around in the yard. This is what the James Webb Space Telescope is going to allow us to do. It's going to see those smaller, fainter objects. And it's really exciting because we believe that there's different types of these black holes in the beginnings of their lives that then grow over time to form the different bigger scales of black holes we see today. Because we see a huge range from small black holes to medium black holes and giant black holes weighing billions of times the mass of our sun. So James Webb wants to put this family picture together of the birth or the baby black holes to the adult grown black holes we see today. So I hope you enjoyed this black hole catch up and update, and make sure to subscribe on YouTube to stay up to date for space.